So first, it's great to see so many rabid Haskellers out in force the day before Thanksgiving. It means a lot to me. My dad was telling me, "Oh, Edward, I'm really afraid no one's going to show up to your talk." But I'm happily disproving him. Second, despite what the title slide looks like, this work wouldn't be anything without my lovely collaborators. So Scott Kilpatrick, in particular, who was a PhD student at MPI SWS, but is now here in New York, and also Derek Dreyer, Simon Payne-Jones, Simon Marlowe. All these people were very important in the formation of this work, and so I owe a lot of intellectual debt to them. So what do I want to tell you about? Well, it can all be summarized up by this one slide. First, Backpack is a mixin package system. I guess this is not a very good summary because what's the mixins, what's packages? I'll tell you what that is. Two, it's actually shipping with GHC 8.2. Like, it's merged ahead. We haven't cut the 8.2 release branch yet, but when we get there, it will actually be there. So that's pretty cool. And sort of the big idea and the sort of thing that was sort of the main idea that came out of this work on Backpack is how do we factor the design of a module system, a package system that allows for parameterization in a language agnostic way, and also split it into two parts, a language agnostic part and a language specific part. So the reasons why you want to do that also I hope to explain in this talk. So broadly speaking, I'm going to tell you about why you want a module system in Haskell in case you weren't convinced by Gersham's introduction. Two, I'm going to tell you how Backpack works and also interleave that with a demo because this is all real code. This is all stuff you can actually run today. And finally, well, we'll see if I have time. I'll tell you about some of the stuff we've been doing with Backpack in the Haskell ecosystem. So first, why do you want a module system? So, if you just sit down and look at it, look at your code, think about it, there's actually opportunities for modularity everywhere. And obviously, I can't talk about every single opportunity, but I want to give you a few. So this one, I actually got this idea talking to an engineer from Google. I was telling him about Backpack, and he told me, oh, when we write software at Google, we really need to be able to swap out our components. We have some production version of a component which actually talks to a real service, but when we want to test, we don't want to actually use that component. We want to use some simplified mocked version, some stub instead, which can run faster, doesn't actually send emails to all our clients, and will actually let me do this, right? And so, in most languages, it's sort of, you want to be able to switch between the real service and the mock service. And so in most languages, there's not really that good ways at the language level to actually achieve this. So, here's from a blog post describing how to do mocking in Haskell, and what is their suggestion? Their suggestion is, oh, well, Haskell is a higher order functional programming language. The way you can mock things is just create a record representing all of the operations that you might want to mock, and then just make two different implementations of this record, one with the actual implementation, one with a fake implementation. Okay, that's great. It works actually reasonably well. But there are some problems, right? One is you have to, plumb this, special data structure throughout your code. And another is that you've introduced some sort of dynamic indirection in the process because, now the compiler doesn't know exactly what operation you want to run when you're sending and receiving. So maybe if you're not calling these functions very often, that's not a problem, but it's not a cost-free abstraction. And so, people think, oh, well, maybe I shouldn't abstract my code in this way because my code is going to run slower. This scene plays out again and again in every single language. Like in Java, you have to decide between, using some dependency injection framework or using the actual class directly, and you often end up adding dynamic dispatch even when in production you don't care about it. And that little bit of performance often adds up. Okay, let me give another example. So in the Haskell ecosystem, there's this well-known sort of problem called the string problem, and a good way to demonstrate this problem is to look at one of the existing libraries in the ecosystem. So here's the Unix package. So this is one of the boot packages that comes with GHC. You say, oh, well, if I want to use any POSIX APIs, I'll just depend on the Unix package. And if we look at the module listing on Hackage, we see something very curious. All of the modules occur twice. Once, normal, and then once with byte string appended to the end. And if we actually take a look at the code inside these modules, they're actually substantially the same code. So here's an example. It's getEnv. What does this function do? It just gets the value of an environment variable according to the POSIX API. So here's the string version. What does the string version do? Well, it takes in a string, which is the name of the environment variable, and returns, if it exists, the value of that environment variable. And it does some operations on it, and does it. And then here's the same version in the byte string version of the environment module, which just takes a byte string and returns a byte string, but otherwise does exactly the same thing. And there's some differences. There's some different calls to internal functions which implement important operations on the string type, but basically the code is substantially the same. And so, this is Haskell. We live in a language where, abstraction is something that we really care about. Like, we really care about being able to abstract when we want to. And so code duplication like this should be a really bad sign. And, here's an example of a bug that I found while I was doing some backpack work with the Unix package, where there was an implementation of putenv in the string version and an implementation of putenv in the byte string version, and the byte string version had a bug. Basically, there's some tricky business with memory ownership that you have to be careful about, and the string version did it correctly, the byte string version didn't do it correctly, and apparently no one had noticed because I guess no one really likes using the byte string version of functions. So I don't think I need to say very much to say, code duplication is bad, and sometimes our programming languages don't make it easy for us to eliminate code duplication. Okay, so let's look at this problem more broadly. So the more broad problem with strings in Haskell is that you've got these two packages, byte string and text, which have different representations, different trade-offs about what sort of you want your strings to represent, and when you want to write a library that just gives some sort of generalized string processing functionality, for example, autoparsec as a great example, you have to write the package twice, once for the byte string version and once for the text version. And you might consider using a type class, you might consider using one of these explicit records to modularize, but if you're a language like autoparsec and you really want to be fast, well, that's just going to be too much performance hit to bear. And this is not like hypothetical. So Reflex, which is a FRP library, one of the problems that they are trying to solve is that they can't get GHC to specialize their instances because they've got this type class which lets you parameterize over the implementation, and it's nice because it lets them swap things out, but then inlining doesn't work and their code runs slower, and that's not great. To make matters worse, any other package that depends on autoparsec themselves have to be written multiple times. So, this is kind of terrible. And in practice, not even all the implementations are written. So have you ever been in a situation where you wanted to use some Haskell library, but you couldn't? Why couldn't you? Well, because someone had decided to only make it working on text. And, byte string, oh, what are byte strings? Like, we're UDF-16 data. Why do I care about byte string? Even though there isn't any good reason for them to, commit to an implementation at that point in time. And let's talk about something else. So recently, there was this new library release called Foundation. So what is Foundation? It's just yet another prelude because everyone loves their own custom Haskell preludes. But one thing that it did, which a lot of people liked, was it defined a new string type, as if we didn't have enough string types already. And what was Foundation string type? Well, it was, we want UDF-8 encoded strings, because UDF-16 is horrible, like you're paying a 2x performance space expansion for ASCII data, and usually that's not a good trade-off to make. And yeah, so the uphill battle the Foundation folks have is that, well, they're going to have to re-implement the entire package ecosystem, but replacing, text with Foundation. And who has time to do that? Like, it's just too much. So here's the situation, right? So if there's nothing else that you take away from this talk, it should be why, modularity is useful. So the situation is that, the ability to parameterize over implementations, over types, that is a really useful capability. But when we look at traditional programming language mechanisms for doing so, we always find that the ability to parameterize comes at a cost. You have to make a deal with the devil. And the cost either, is, or often both, is in the code you write. The code you write looks less, beautiful because you have to now pass around structures around, or, like gunk up your type signatures with extra type variables. Or it comes at a performance cost. So now where you previously could do static dispatch, where you could inline in the compiler, you now have dynamic dispatch. And there's also a problem where if you try to eliminate this by specializing the code, you often end up with a lot of code duplication. And so, those of you who write C++ every day might say, well, templates don't have the dynamic dispatch problem because they always get expanded. Well, but with templates, you always end up, recompiling the template repeatedly every time it's initialized, and only at link time do you actually get to, eliminate the duplicate code. So, what we can say is that, the problem of, parameterizing code, it's most difficult when you're trying to parameterize a large body of code. If you're trying to parameterize an entire, graph of packages, all of which, depend on some basic type. And arguably, that's the point where you really do want, some capability of parameterization, because, modularity and features for modularity and encapsulation, those are not features that are that useful when you're writing small programs. They're useful when you're writing large programs. So, the inability to use these language features at the scale where they're most useful is a giant missed opportunity. So what can we do? And I wouldn't be here if there was something that I could sell you, that I could say, well, there is something we can do. And the answer is Backpack. But, what do I mean by Backpack? Well, we're going to bring modules to Haskell with two good ideas. The first idea is we're going to late bind modules. So this is pretty normal. Like if you know ML modules, if you know dependency injection, all of these are predicated on the idea of not committing to a specific implementation until you know better what implementation you want to use. But the second idea, and one that's sort of very novel and sort of not, even in the early precursor work that Scott and co, put out, it wasn't really emphasized as much as it should have, is that we're going to do this in the package manager. And as we're going to see, this is really, really weird. Like very strange, but it actually gives us a lot. So hopefully I can convince you that this design decision actually is a good one and is actually going to give us payoffs that we want. So let's just set the basic ground rules. So what do I mean by late-bound modules with types? Well, in Haskell, you can write modules. So with Backpack, you can also write signatures. So what's a signature? A signature is some sort of requirement. It says something that I don't know the implementation of, but it needs to implement some types. It needs to implement some functions. So to continue on with our parsing example, the signature for strings, it defines some type, some abstract type. I don't say how data is implemented. And it defines some functions on that type. And the fact that I have a signature means that I can type check this autoparsec indef package without knowing any particular implementation of the module in question. What's next? Well, clearly it's not useful to just type check my code. I also want to run it. So what I want to do is I want to create some various packages for the implementations that I want. The convention I'm going to have is that each of these packages exports a module that's named the same as the requirement I've written here, but there's no particular reason this needs to be the case. It's just for exposition, and also because it makes the code you write a little nicer. And so what are these modules going to do? Well, in the face of an existing library interfaces where byte string names their type byte string, text names their type text, we just need to sort of smooth out the differences so that they all export the same thing. And now, to implement this, to fill in this requirement on autoparsec with an implementation, all I need to do is so-called instantiate the package with the implementation of the signature that I want. So the way that I actually do this in real cabal is, in this case, it's very simple. I just say, well, I want autoparsec indef, and I want text. And so long as text provides a module named stir and autoparsec requires a module named stir, we automatically know that the text is going to be implemented the requirement name stir is going to be implemented using text. And we get basically exactly the same library as we had before we didn't do any of this nonsense. And so the only thing that we need to do when we want to hook up a module in this way is we just have to check if the module provided implements the signature that is required by the package in question. And that's the only check we need to do, and then the hope that we have is that after we do that, the rest of the package will compile well. So another idea is that you can use these signatures and you can distribute them to your upstream providers and say, hey, this is the API I need. If you change it, please let me know because this is what I'm depending on. As a side note, in Haskell, we can't actually get this guarantee all the time. It's literally impossible. And it involves open type families. So I guess if you're interested, ask me a question and I'll tell you more about it. So that's pretty simple. And if those of you who know ML modules might be thinking, oh, this just sounds like ML modules. What's new? And so one of the important things that we want to hold for a module system is that it needs to be compositional. What do I mean by compositional? Well, it's not enough to just write some code, parameterize it, and then only allow my clients to just use the parameterized version if they provide an implementation. I need to also be able to combine different pieces of code which are parameterized in this way and keep the parameters. So in this example, if I'm talking about the DDD package, which was my example of a package that depended on autoparsec, if it doesn't want to commit to a specific string representation, it should be possible to depend on autoparsec indef and not actually say how a string is going to be implemented. And the requirement should simply be inherited through to the parent package. And in a more complex example where I have multiple packages which depend on string this way, well, those requirements should just get merged together. And so there's a single string interface that I actually care about. So, so that's it for, the basic ground rules of Backpack. Hopefully there was nothing ground shattering, nothing ground shaking. Like it's not that hard to understand, honestly. And so now I want to tell you about the other important design point about Backpack, which is that it's done in the package manager. And the reason we want to do this module system at the package level is because the package manager already does many of the things that we want our module system, our ability to parameterize code, already. For example, when we run the package manager, it's responsible for making sure that if two packages depend on the same package, I only compile that package once, and I don't duplicate the code in those cases. And a similar problem arises when I am parameterizing some code. I instantiate it one way by one person. Another person instantiates it the same way. Well, I don't want the code to be duplicated in that case. And so if the package manager is responsible for building these parameterized packages, it can automatically do the deduplication, sort of no extra fuss needed. Another thing that we want to do is that if we parameterize an entire package with one of these requirements, well, someone who is going to decide to instantiate it needs to know about packages. And really, the compiler doesn't know very much about packages. That's a sort of meta-linguistic abstraction. So the only person that really can handle packages is the package manager. And so what is the payoff? The payoff is one that when we write packages in Backpack, we don't have to pay any performance cost because what the package manager will do is compute the entire graph of instantiations and then compile the code for each instantiation directly against the implementation. And so inlining, all of your good stuff can happen. So you should not pay a cost if you use Backpack as opposed to if you import the module directly. And as I said, this allows us to bring modularity to the biggest scale of programming that we do in Haskell. And also, it gives a really good story for backwards compatibility because you can take existing package like autoparsec, you can parameterize it, call that a new package, autoparsec in def, but then you can instantiate the package and get back the old package that old consumers of the library expected. So really helpful because not everyone is going to move over to using Backpack all at once. Okay, So if those of you who nodded your heads and said, of course, module systems should be in the package manager, I want to now emphasize the fact that this is actually really weird. Because the way that most compiler writers go about adding new features to languages is they say, well, what am I going to do? I'm just going to, do some change to the compiler, and now I'm going to have, I'm going to have a new feature, and we'll add a new language pragma, and everything will be great. But when I came into this project, I thought, oh yeah, this is going to be easy. We're just going to do a hack on the compiler. I'll finish it by the end of my internship at Microsoft Research, and everything will be great. We'll have a great paper, and then I'll move on to other things in my PhD. Well, no. So what's the problem? So the problem is, traditionally, the way that we design our sort of tool chains from package manager to compiler is that we have this abstraction barrier between the package manager and the compiler. And this has been pretty important because it's let people like Stack implement a different version of the package manager without re-implementing the compiler from scratch. And so the way that this abstraction barrier works, and sorry Connor McBride, I stole your characters, is that the package manager knows nothing about like the Haskell source language. All it knows is about how to call the compiler. It knows about the global picture. It knows about all of the actual packages, all the code that's going to be assembled, but it doesn't know anything about the code itself. And the compiler sort of does the dirty work. It knows what the source code is, and it knows how to actually compile it, but it has a very narrow, localized vision. It only ever knows how to compile one piece of code at once. So Backpack and any sort of module system, well, it really wants to break the abstraction barrier between the package manager and the compiler, and that's hard. And the reason why it wants to break the abstraction barrier is because all the different components I've told you about, well, they actually can only effectively be implemented in various different parts of the package manager compiler divide. For example, this problem of separately type checking code against a signature instead of a module, well, that's definitely the compiler's business because the package manager knows nothing about type checking. But on the other hand, this idea about deduplicating libraries that are used multiple times, that's something that the package manager handles because the compiler, is just going to build the code that you told it to build. It's not going to know anything about reusing code in this way. So we have to disentangle, this sort of interwoven, set of concerns so that we can preserve the abstraction barrier. I suppose someone could tell me, oh, Edward, you should have just, put GHC and Cabal and Stack into one, giant blob of software and that would solve your problem. And it's true, it would have solved my problem. But I think a lot of people would get very unhappy at me for breaking that abstraction barrier. So the Backpack challenge is to figure out how to set things up so that we don't need to break the barrier, that we can preserve the abstraction barrier between the package manager and compiler. Of course, it can be done, and the sort of punchline is that if we think about the GHC command line interface as a programming language in its own right, we can design a sort of lower level version of Backpack which is very unpleasant to program in directly, but is very simple for the compiler to do. And the basic ideas are that for every package we want to compile, I've named them components for reasons that are not important for the talk. We say what the required signatures are. We say what its dependencies are with explicit instantiations of the parameters on them. And we can also specify what the signatures and modules are. So now is a good point to skip to a little demo that I want to do. I apologize, I haven't ever run this demo in its completion on this particular platform, so there may be bugs. Please stand by. So what are we going to do? So I want to show you first how we actually program with Backpack. And it's going to be awkward holding this microphone, so I'm just going to shout. So in this file, oh, thank you. Okay. So in this file, I've kept some code it's not exactly important what the contents of this file are, but I need to talk about some of the features of this file. So first of all, this is a BKP file. So the BKP files are a kind of new thing that are coming in GHC 8.2. You should basically not ever use them because in real software, it's not what you want, but it's really useful for experimenting with Backpack and also seeing this sort of intermediate language which has explicit instantiation. So I'm going to do the first part of this demo using this BKP language. So how does the BKP language work? Well, it looks very similar to normal Haskell, but there's this new top level, and the new top level is that we declare units. And units themselves contain modules, and I can declare as many modules as I want in a unit. And I have to do them in order, and otherwise, so a unit is like a package, and I can define multiple units in one of these BKP files. And so what do I have here? Well, what I have is a package named regex. It defines a module named regex. Which defines a type for regular expressions, some functions on how to do it, and then I have another package named main. It depends on regex, so think about this like the package ID flag to your compiler, which says what packages to bring into scope. By the way, if you've got questions, please shout. Like, yes.
If you didn't point this out right, note that these are multiple modules all defined in the same text file. So that's coming here, right?
Well, but you shouldn't actually use it because like. It plays very poorly with incremental compilation. Like you need to know if a file is changed to decide whether or not to recompile it. But if everything is in the same file, you don't get as accurate recompilation. So you shouldn't actually use it for your projects, just for demo purposes. So what does this main function do? Well, it defines some regular expression and it prints it. So the details aren't important, but what we're going to do is we're going to take this module and we're going to parameterize it over the string implementation because I've been talking a lot about strings, so why don't we go and do this? So what are we going to do? Well, why do I have a change to this file? So what we're going to do is let's first rename this module to regex indef. And let's start writing out the signature for what we want strings to be. So, signatures are signified with the signature prefix instead of module. And, I want a type named string. And I need some operations on this string. And so one of the important things is that I need this splits operation and this parts operation to work on my string. So let me comment out this code for a moment. And why don't I put in these type signatures? So whatever the string is, well, it needs to support partitioning. And whatever the string is, it needs to support splitting. And I have very bad memory, so I think what parts does is it returns all unique partitions of the string of as many partitions as you want, and splits basically gives you the version with an empty string and then the whole string and then one string and then one and after the string and so forth. So those are some operations. Next, what I'm going to do is I'm going to have the module import string because it needs to use the operations from string. And then we'll change some of the type signatures. And let's try to compile this. So the way that I compile code like this, let's see, where? Yes, thank you. What should take an argument? What's the question? Splits? Yeah, it should take an argument. Thank you all. So the way I run this code is, so I need a head version of GHC, so this is compiled pretty recently, and I'm going to use the -- backpack flag. I'm sorry, it's kind of cut off, but once it scrolls down, you'll be able to see it. And I'll try to run regex.bkp. And actually, I purposely put some errors in here because they're very instructive. So the first error is that we couldn't match the expected type of null with stir, and the reason for this is null is parameterized over traversable containers. So, well, that's not going to work because we don't know if stir is actually a traversable container. And for byte string, it really isn't. So if we want to allow byte string. And the second one is, well, we assume that it's actually a list of cars, but it's not. So the way we're going to fix this problem is we'll just introduce some more functions. So let's introduce singleton, which takes a car and turns it into a stir. And let's introduce our own version of null, which takes a stir and tells us if it's empty or not. And so now all I have to do is, I have to hide null from prelude, blah. And I am going to, this null will use the right one. This thing will, I'll just say singleton. There's one more error, which is I need a type class instance for equality on strings. So let me just declare that's something I need. And now, oops. So another reason you shouldn't use this code is because it's got lots of panics and not very good error messages because it's not supposed to be used. And I just need to, let me comment out this code for now because it's not going to work yet. So now when I run regex in def, what we can see is that we've type checked the code successfully. And I actually didn't say what string implementation we wanted to use. And so in this situation, we can't actually compile the code because we don't know what the implementation is. So this makes Backpack a bit different from module systems like ML, where there actually is some compilation that goes on with functors. And the reason why we defer the compilation is because, as I said, we want inlining. We want to know what the actual implementation is when we actually build. So we can't actually build until we know the implementation in question. So that's okay. I'm going to skimp out on the part of the talk that talks about how Backpack works because I think that I actually want to do this demo to its completion. So let's actually give an implementation for string. So we need to, so I'm going to put this in another package. Let's call it stir string. And we're going to make a module named string. And so what things do we need to implement? Well, we need to make sure that the data type is implemented and all the operations are implemented. So let's first define the data type. So we're going to say, well, a stir is just a string, type synonym, so we don't have to wrap, unwrap. This gives us the instance for free. Let's grab our implementations of splits and parts. And stick them in here. And we'll have to implement singleton. And one of the sort of warts of Backpack as implemented today is you have to exactly match up the types. So I couldn't just write this without a type signature. That wouldn't be acceptable. And the other function was null. And let's just hide preludes null. And let's run it. So first let's see if stir string type checked. It did, but I didn't say that I actually wanted to instantiate it. So what am I going to do down here? Well, let's bring back the code from main. And so we want a dependency on regex in def, but we want regex in def with the string using the implementation from stir string. So what am I going to write here? I'm going to write, well, the requirement named stir should be implemented equals with stir string stir. And this should compile, and it should run. So we've got unparameterized modules. Okay, quick poll. So who would like me to move on with the rest of the talk versus now showing you how to do this example with Cabal? Because this is a toy, and you actually want to actually write packages if you're actually wanting to do this. So move on with the talk. Continue the demo. Okay, let's continue the demo. So now let's make a new directory work. So this is all very nice and good, but as I said, BKP files are not very practical for real-world use. So what are we going to do? Well, we're going to write a new Cabal file, which is going to implement all of Backpack features. So let's call this regex equals C because it's going to compile an executable. Build type simple, Cabal version, greater than or equal to 125 because we need Cabal support, and version 1.0. And so let's just start off with the library. So the library, there's a new feature in Cabal which is private libraries. So you didn't used to be able to put a name after a library, but in 8.2 you will be able to. And so what does this do? It just lets me define multiple libraries in a package, because I could make separate cabal files for every single one, but it would work, but it's annoying, so I'm just going to do one. So what are the exposed modules of regex in def? Well, it's going to have a module named regex. What are the signatures? It's going to have a signature named stir. Build depends is going to be base, and that's it. And let's just put that in to make cabal shut up. Okay, there we go. So, I want to put this in its own source directory. So mixter regex and def, and let's set up these modules. So I need regex.hs. So let's pull up our regex.bkp to do some copy pasting, because everyone loves copy pasting. I know I'm such a hypocrite. So here's the regex module. Dedend it so that it looks normal. It's just a normal module, no problems. And let's also bring in the string signature. Also no problems. And let's build it. So one of my little sins is that I didn't make this work with the legacy Cabal install codebath. So you'll have to use this new feature in Cabal called Nix style local builds. It's great. You should use it. It saved my PhD. Like I literally would not have been able to develop the Cabal changes without this little piece of tech coming about. So I'm just going to ask it to build. And so it's going to do some stuff. And it's telling me that my compiler is not new enough. And I really do need to give it a compiler that's new enough. So let's use GC head. And as before, you can see from the output that it's not actually compiling any code. It's just type checking. So that's good. So let's keep going. So let's bring back this module. Let's make stir string. So this one's a very normal looking module. Let's just copy this and stir string and make dir stir string, make stir.hs, bring in the code. And let's just make sure it compiles. So you can see now we're building stir string. This one we're actually going to build because we don't have any requirements, so there's no problem. And so now let's put it together. So let's call it an executable. So this is interesting. So I'm going to put in the normal accoutrements of an executable. So, we're going to say what the main is. I guess we can also say what our build depends is and what our language is. And so we want to use this regex package, and we want to use it instantiated with stir string. So what are we going to do in this case? Well, you could imagine writing the same, direct, syntax for instantiating the dependency in that way, but that might get pretty annoying the more signatures you have. And we want to encourage a mode of development where you write as many signature files as you need to specify the requirements. So here, the idea of mixin linking comes in. So what we're going to say is that if the module is named the same as the signature, and you bring them into scope using a build depends, we'll just automatically instantiate it that way. And you can rename modules so that things instantiate or don't instantiate as you want. I won't tell you that syntax, but in this case, everything works out nicely. I'm just going to depend on regex in def, and I'm going to depend on stir string, and let's see if I did any typos. No typos. So something interesting to see here. Let me. I don't have to scroll up. So here we see that there's one version of regex lib regex indef showing up, but there's another copy showing up here. What's that second copy? The reporting is not so great right now, but that second copy is regex indef instantiated with stir string. So we have to go and actually compile it again, and we actually do so, and we end up with regex.o. So this didn't actually work because I didn't actually put in main.hs, so let's just stick that in real quick. And so now it's compiling main, and we can copy this very long executable path and give it a run, and it does in fact report the correct answer. And so there's plenty more you can do, like you can try putting in a version of string that's byte string, and that'll work as well. And you can also try splitting up the signature into two parts, because you might not want your strings to just only be characters. You might want them to be parameterized over any arbitrary element value. The sky's the limit. Like one of the problems with working on a system as general as a module system is it's hard to say what it's actually going to be useful for before it's actually out there. So one of my goals in this talk is to convince you that Backpack is actually kind of interesting, and if you have any projects which are tracking ahead of GHC, hobby projects maybe, you please give it a try, because your feedback is going to help make Backpack as good as it needs to be to sort of take over the entire Haskell ecosystem. And that's where I'm headed. Not in the next year, but maybe 5 years or something. Yes?
If I'm like the maintainer of Adaparsec, and I want to write a test driver for Adaparsec.
Yes.
How can I make sure that now I can test against most of the string libraries?
Yeah, so that's a great question. I think right now the most reasonable thing for you to do is to just know about the string library somehow, and then bring in those implementations explicitly, instantiating your test driver multiple times, once for every library you want to depend on. Now, in the distant future, like requiring perhaps extra PhDs of work, you might imagine a way of saying, oh, I have some interface I provide. What are some interface I need? What are the things that actually provide this interface? And you might even imagine using a mechanism like this to give more precise bounds on the packages you depend on, rather than some sort of version range. Well, in addition to a version range, because there's always semantic constraints that you can't capture with Haskell types. But things to think about. But sort of the thing that you can do today with 8.2 is just instantiate it for each one that you want to test with.
One test driver, I need a test driver.
So you write a test driver library, which is parameterized, and then you'll instantiate it once for every implementation of string you want to run it with. Great question, though. Are there other questions? I love questions. Yes?
So what does it look like when, if I'm on the Adaparsec side, and there are some things that you just copy and paste different string versions in, but there are other things that you don't want to append to large byte strings?
Yeah, that's a great question. So actually, you've seen a little bit about this in the demo that I did. So if you look carefully at my string signature, this splits function and this parts function, they're not actually normal functions in your standard library. Like, I defined them specifically for my application because it was the right level of abstraction that I needed to interact with strings with. And so similarly in your case, you want to write your signature at the correct level of abstraction so that you can be as performant as you need to be. And so this may mean eschewing these low-level combinators like append for, like maybe explicitly specifying, oh, there's some type of builders and there's operations I can use to build strings. And that's just another signature, and there's nothing wrong with that. And so this idea that you can't write a type class for strings sort of comes out of this problem, which is that when you write a type class for strings, you need to decide a priori what methods your type class is going to support. And so if you don't support this very important function, which can be implemented efficiently for some particular representation, well, you're kind of out of luck. Like your code is going to run slower than it could have run. But with backpack signatures, one of the things about the system is it's structurally subtyped. So all you need is a module that provides all of the functions declared in the signature, but you don't have to declare an explicit relationship between the implementation of a signature and the actual declaration of the signature. So, this leads to semantic hazards, right? Like, maybe someone requests a cipher and a null cipher, does in fact implement all the functions you need, but it's exactly not what you want to run your code with. But that's why, mixin linking is implicit, but it is not completely type directed in the same way that type classes are. So also a great question.
So in that headoparsec example, I still have to write both versions of the code exactly the same way. It's just an easier user interface for somebody using the library.
In attleparsec today, in attleparsec today, in the library, they have to write the code twice, once for byte string, once for text. So it's not just users who benefit. Like, you benefit because, as long as, you don't have to, extend the level abstraction to the entire parser library. And this is definitely not the case. Like, there are definitely bits of shared code between the two implementations. That can be shared in the backpack world. Other questions? Yes?
How about the lazy versus strict and byte string?
Yeah, totally. Like, obvious application, and you don't even have to do any renaming. You can just, because they're both named byte string in those cases.
Still have both lazy and strict in the same package?
Yes. So let's talk about that a little. So I will mime for a moment. So in this, in here I've sort of rewritten the code so it looks a little bit more like the byte string situation. There's no strict string type. I guess you could write one and it would basically look like you expect. And so in this case, if I actually want to use, I'm not going to rename stir here. And so if I want to use the lazy version in my code, I can't actually just say this because the stir module doesn't exist. I have to actually say lazy in this case, right? So what does that translate to in the cabal level? So this is like the abstraction barrier working at work. It's cool. In the actual example, I saved it. Now string is going to be stirred lazy. And so now the names don't match up. So I need to actually, do some impedance matching to say I want string lazy from the string package. So now I use this nifty new keyword called mixins, and I say, well, there's two ways I can do it. So one way I can do it is I can say, well, I wanted regex indef, but I don't want the requirement to be named as string. I want to rename the requirement to string lazy because that's the name of the module I actually have in my code. And so now if I run this, what happened? Oh, that's because I need to actually move the string module to the correct place. But I guess I don't have to complete the example because it figured out how to instantiate everything. I'm missing a source file, but that's easy to fix, and it's not germane to the question. So even if I hope I interpreted your question correctly, but even if I, name things lazy and strict, I can still feed them into the requirement simply by renaming the module or renaming the requirement. So there's another way I could have done it, which is bring stir string into scope, but rename stir lazy into stir, and that uses similar syntax in that case as well. Yes?
So taking it a little bit further, could I have, could I use a signature and use it as two names and instantiate it in the same program?
Oh, yes. So let's see. So is your question, can I take a signature, take a package with a signature, and then use it twice, but naming the signature differently in each case? I can absolutely do that. I'm not going to demo it because it takes a little bit of setup. But so in the intermediate language, so the BKP file, that's as simple as saying the dependency multiple times, but instantiate the dependency with a different parameter in those cases. So if you know what the implementations are, you can like fill in one implementation and fill in another implementation. If you don't know the implementations, you want to pass them on, there is a different syntax using angle brackets for saying, oh, fill this in with a requirement named A, and then fill this in with a requirement named B, and that'll do what you want. At the cabal side, once again, this mixins field comes into play. So in build depends is primarily for doing version bounds, and so every package only ever exists once in build depends. But mixins is all about saying what my dependencies on the component are. So a package can occur multiple times in the mixins field, and so every time it comes into play, it gets fresh signature bindings. And so if I don't rename the signature, they'll all get merged together because they have the same requirement name. But if I rename the signatures, now I can have two sets of requirements which I can pass on or implement differently depending on how I want it to. So you can do that. Other questions? I love these questions. They're great. Okay, so let me just wrap up the talk portion. So I could tell you all about how compilation works in GHC, but I've told you the main points. The main points are that when we compile a package in Haskell, the way that it actually works is that we if you ask cabal install autoparsec or stack build, it first figures out all the packages you want to build and then calls the installation process on each of those packages. Those build things actually call out to ghc-make, and ghc-make internally calls a one-shot compiler on every single module in the project. So we can sort of represent this in our sort of language version using a dependency for every package we depend on and a module for all the input modules to the compiler. So if we want to extend it for Backpack, we just need to extend this language to also support signatures. And we need to support it to extend these explicitly instantiated packages, which we translate from this implicit language into this explicit language in the package manager. And other types of merging, well, those get handled by the compiler. So for example, if I have a package which defines a signature, another package which defines a different signature, I want to put it together, well, the compiler can look at the dependency flags passed to it and determine how the merge should go. And so we end up with the sort of abstraction that I showed you, and that I showed you that you could program with explicitly using BKP files. But once again, you shouldn't. Use cabal files, use the implicit version, it's better. So what have we done with it? So Backpack is really new. Like, it landed a few months ago. I don't know anyone who has written a real package with it. I published a blog post saying how to use it, and I know at least 2 people have actually run the code besides me, so I guess that's a start. Really, it's up to you guys to push this forward and show that this is something that is worth dropping your support or forking your project so that you can use these features. So I've done various backpackifications of packages of varying shapes and sizes. So the Unix example I gave at the beginning, well, that can be backpackified. I won't show you all of it, but the important thing is, the interface I needed for strings doesn't look that much different from the one I demoed. There's some, extra fancy functions for, actually marshalling things to and from the C FFI, but otherwise, the changes were pretty straightforward. Another example, which I got off of Reddit, was someone had this package called TagStream Conduit. Like Unix, it's got 2 versions of the package, one for text, one for byte string. Well, we can backpack it. So this one needs 3 signatures. It needs a signature for strings, a signature for builders, and a signature for parsers. But it all works. Like you just define one of the signatures, and the other signatures import the other signatures, and otherwise everything works out very nicely. So Backpack is a mixin package system. It lets you parameterize packages by signatures. You give the types for the signatures. You can type check without an implementation, and later a user can decide to instantiate it however they want. It's shipping with GHC 8.2. If you use HVR's PPA, it's an Ubuntu PPA that has various versions of GHC. You can download GHC head and try it out for yourself. You'll need a new version of Cabal install, but just download Cabal install, build it, and you'll be download the Git checkout of Cabal install and build it, and you'll get the most recent version. And what's the big idea? The big idea is that package modularity is too important to be limited to the compiler. So bring modularity to the package system, figure out how to preserve the abstraction barriers, and have a lot of fun. Thank you very much.